now about 4 different functions and 4 different pole zero patterns and 4 different regions. And I want to think about the defining integral, that one up there, right? I want to think about x of s is the integral over all of time of x of t e to the minus st dt. What are we doing when we take a Laplace transform, and what are we doing when we specify a region of convergence? Because that can help you think about what should the answer be, which is helpful when you're trying to think about, does my answer make any sense, or what am I doing anyway? So x1, this was e to the minus t. So it had a pole at -1 and the region to the right. Right-sided function, right-sided region. Here, we have a more complicated function, which can be the sum of 2 poles, one at -1 and one at -2. And we got a region that was to the right of the rightmost pole. Right-sided function, right-sided region. Here was x3, which was the negative part of that one. We got the same pole at -1 in the left-sided region. And here was the symmetric one, where we found that the region was in between. So what I want to think now is what happens when we have a particular value of s that is inside or outside those regions? What's really going on? So let's start by thinking about what would happen if I considered an s depicted by this red x. I probably shouldn't have used x. I should have probably used a star. That's not a pole. That's the value of s in this integral. What happens if I choose to integrate against the function e to the minus st where s is 0? If I choose to integrate against that function is depicted by red here. So the convergence of the integral, the convergence of the thing that I'm calling a Laplace transform, depends entirely on the convergence of x. That's what s equals 0 means. S equals 0 says the convergence of the function, the convergence of the transform depends entirely on the convergence of the function. So that means that this function converges. It's in the region of convergence. This one converges. It's in the region of convergence. This one does not converge. This one diverges. As you go to minus infinity, the function is unbounded. The transform doesn't exist. S equals 0 is not in the region. That's what it means. Here, if I integrate against e to the 0, both sides converge. There's no problem. I'm in the region. Okay? So now if I think about a different s, what if I move s a little bit to the left, say -1/2? If I'm thinking about integrating against e to the minus st, and if s is -1/2, that's e to the half t. E to the half t is a function that for all time becomes greater as I go toward positive infinity, exponentially greater. So if I think about what happens if I multiply this x of t by that weighting function, does the product converge or diverge? It converges because the convergence of the blue line is faster than the divergence of the red line. Even though the red line is diverging, the product is overall convergent. Okay, that's because of the relative positions of the red x and the blue x. The blue function is converging faster than the red function is diverging. The product converges. So this x is in the region of convergence. That's what it means. Similarly here, this is diverging. The red curve is still diverging. It's the same red curve. So all these red curves are diverging to the right. This one is converging. It's ultimately converging as the sum of 2 things, e to the minus t and e to the minus 2t, both of which are fast compared to the explosion e to the half t. So I'm in the region. Here, it's exploding in a region of time that I don't care about. And it's convergent for this region of time that I do care about, but it's not convergent enough. So the integral still diverges. I'm not in the region. And finally, this one is more complicated. The integrand, this thing that I'm integrating against, it's always becoming greater as I go toward positive infinity. That tends to be convergent on this side and divergent on that side, but it's not divergent enough to make the function not converge. So I'm in the region. If I make an even bigger pole, so say I put the e to the st, if I put that at minus 1.5, then that is fast enough that it breaks the product. The product is no longer integrable. So this divergent trend is enough to make that diverge. I'm not in the region anymore. Similarly here, I'm not in the region because I've made it fast enough that one of the parts diverges. One of the parts converges, but they have to both converge in order for the integral to converge. Here, I have finally made the left-hand side convergent enough to make the product converge. So that's fine. And here, this is accelerating so fast that although it was stabilizing here, it became non-convergent over here. So the idea then, what I want you to get from this is the idea that you can think physically about what the region of convergence is. The region of convergence is a function that I stick into the integral to make the integral converge. So the region of convergence corresponds to those exponents that make sense for which the integral will converge. Okay, with that vast new insight, this problem is now trivial.